Okay. Good. So, yeah, welcome to the last talk of today, and today it's my great pleasure to introduce Nai-Hui Chia, who is an assistant professor at Indiana Bloomington and will move soon to Rice University. He has done some very influential work in quantum cryptography and quantum complexity theory, and today he is going to talk about quantum rewinding for zero knowledge. And we're all very excited to hear this talk. Please take it away.
Yeah, thank you for the introduction, and thank you for coming to the talk. And today I'm going to talk about quantum rewinding for zero knowledge, and this is based on the joint work with Kai-Ming Zhong, Qipeng Liu, and Takashi Yamakawa. So here is a zero knowledge protocol. So in this protocol, we are given given the verifier is given input X, and here's the prover. And the verifier wants to decide whether X is in L by the help from the prover. And of course, for this kind of zero knowledge protocol, we need three properties. First, the verifier wants to know whether X is in L because this is his goal. And the verifier also wants to ensure that P cannot cheat. For example, if X is not in L, then prover should not be able to convince the verifier that X is in L. And the last one is that P may not want the verifier to learn anything other than the answer. For example, here, the prover may have the answer like X is in L, and also a witness about X is in L. So P doesn't want to reveal its witness to the verifier. And we can try to formalize all these things by completeness, soundness, and the zero knowledge properties. For completeness, which means that for any X in L, the probability that V accept should be greater than 1 minus negligible. And for the soundness case, we have two definitions. One is the statistical soundness, and another one is the computation. Statistical soundness means that for any unbounded power prover, we should not accept with probability greater than negligible. And for computation one, which means that for any efficient prover, we will not accept with probability greater than negligible. And for zero knowledge, as we said, we want to say that for any adversary V star can only learn that X is in L. It cannot learn anything else. Okay, so note that here, for the completeness soundness, the adversary is the prover. But for zero knowledge, the adversary is the verifier. And in this talk, we will just focus on languages in MP. So there's a very simple protocol, which is that the prover just sends the witness W to the verifier. And this will satisfy the completeness soundness by the definition of MP language, right? But this doesn't satisfy zero knowledge, because in this case, P will also reveal the witness W to the verifier. And so let's try to define ZK more formally by the simulation. Actually, there are other ways to define zero knowledge, but in this talk, we will just use the definition about simulation. So we said that a protocol has ZK property if it can be simulated, which means that there exists an efficient simulator S such that for all malicious verified V star, such that the view of PV is equivalent, is close to the view of SV star. So here we have V star and the P, and they do some interactive protocol. And they will have some transcript. We want to say that the transcript here is equivalent or say close to the transcript output by the simulator and the verifier. And here are something we need to take care. First, V star may have something called A, which is some advice, or say the auxiliary input. And also the view not just include the transcript between the verifier and the prover, but also some verifier's internal, the residual information. And we want to make sure that both the exchange messages and also the residual information are close. And for the simulator, it has some properties. First, it doesn't know the witness W. And usually, its power is bounded. And also, but it has an additional power that the prover doesn't have, which means that it can compute, it not can just compute the V star, but also uncompute the V star. So we say this means that the simulator here can rewind the verifier V star. And the goal of the simulator is try to output some value close to P. And now that here, usually we want SMV should have the same computational power, because the simulator's power implies the information V star can learn from the protocol. For example, if we have a simulator, that power is more, it is more powerful than the V star, which means that after this protocol, V star can learn something that it cannot learn by itself. So to make this definition fit neural knowledge, we need to make sure that the simulator's power is the same as V star's power. And now this is a classical definition about neural knowledge. I want to talk about the say post-quantum neural knowledge, or say how about the adversary is a quantum adversary. So there could be something different. First, because your verifier becomes a quantum adversary, so your simulator can also have the power of quantum machine. Because we say that S and V star should have the same computational power. So now you can have a quantum simulator and a quantum verifier V star. And because now you have a quantum verifier, so it can also have some quantum auxiliary input, so some quantum advice here. And this actually causes no trouble when you want to prove some neural knowledge thing. And so for the view, they exchange messages, and also the residual quantum state of the verifier. So right now, the residual information not just a classical thing, but also a quantum thing here. And for a simulator, it doesn't know W, which is the same, but it can quantumly compute V star and uncompute the V star. So right now, the interaction between S and the V star will be quantum message. But the protocol itself is still a classical protocol, which means that the message exchange between P and V star is still classical. And the goal of the SV star is try to output the classical messages. But their interaction, or say the query from S to V star, could be quantum. Okay. And right now you can see that because both V star and the S get more power to cheat and also simulate, its relationship to the classical neural knowledge is actually unclear. So let me talk about some results about neural knowledge protocols for MP. So about constant run. So in this talk, we focus on constant run protocol. So the first theory is by Warwick and Khurana in 1996. They show that if there is a collision-resistant hash function, then for all languages in MP, there is a constant run black box neural knowledge proofs against any PPT verifiers, which means that there is no BPP algorithm can break, can steal some information from the prover. And then Watros in 2005, he showed that if you assume the quantum one-way function, then you can have small omega 1 round black box decay proofs against quantum verifiers. And this is because its protocol cannot achieve the negligible soundness if they just use constant run. If you want to achieve negligible soundness, then it requires super constant run. And later, by Vidick and Shumley, they showed that actually you can have a constant run protocol if you use non-black box techniques, which means that the simulator needs to know the codes and something about the verifier, such that it can do something other than rewinding. And they show that there's a ZK argument against quantum verifier by just using constant run. And then in this work, Chang and Yamakawa, we show that if you assume quantum LWE or quantum one-way function, then you can get constant run black box epsilon ZK proof or argument against quantum verifier. So here, we can get many things, but we cannot get the negligible zero knowledge. So here, epsilon ZK means that the view of the prover and the view of the simulator has a noticeable difference. But this noticeable difference can be, you can set it as a parameter. So you say that you want to do epsilon, then probably your runtime of the simulation can be 1/epsilon to some polynomial, some constant. Okay. And later by Lombardi, Mar, and Nick, they showed that actually, Khurana's protocol, like their proof here, is secure against quantum verifier with coherent runtime expected quantum simulation. So this simulation is, in my view, is slightly more powerful than the quantum polynomial time simulator. But it's still a very interesting definition because even given the verifier this power, it cannot break any node primitives we use to build the zero knowledge. But it's slightly more powerful. So you can see that classically we have a very clean theory in saying that constant run black box zero knowledge proof against PPT verifier exists. But in the quantum setting, we have many results, but all of them cannot reach this clean and beautiful theory. So we need to relax something, satisfy something, or use additional information to do the rewinding. So now the question is, can we have post-quantum O1 round like BBZK proof or argument? And the answer is actually no, unless MP is in BQP. Okay. And so here is the plan for the talk, for the rest of the talk today. So first, I will tell you the challenge for quantizing classical ZK protocols. So I will quickly review Khurana's ZK protocol for MP, and then I will tell you why it is very challenging to show that it is quantumly secure. And I will also talk about the impossibility, and then I will tell you how to prove the impossibility of O1 round post-quantum BBZK for MP. So for the proof, there are two steps. The first step is to show the impossibility of strict polynomial time simulation. So here, strict polynomial time means that the algorithm always outputs answer in a fixed time queue. And then I will show you how to lift the impossibility result from strict polynomial time to expected polynomial time. And here, expected polynomial time means that the algorithm might sometimes not go into exponential time, but it stops in polynomial time on average. Okay, and in the last we'll discuss some. We will have some discussion, and I will tell you some open questions about the quantum zero knowledge. Okay, and let's start from the ZK protocols for MP. This is the classical protocol. So here we consider a Hamiltonian cycle problem. So this is a fundamental problem that you are given a graph and you want to decide whether there is a Hamiltonian cycle in the graph. And this is an MP complete problem. And Khurana gave a constant run ZK proof for the Hamiltonian cycle problem. And because Hamiltonian cycle problem is MP complete, so all languages in MP have an O1 run ZK proofs after having the ZK protocol for Hamiltonian cycle. And their protocol actually depends on the commitment scheme. So commitment is a crypto primitive that has two properties, the hiding and the binding. So you have a message M, and you want to put it in some envelope. We call it com-MPP. Okay, the hiding means that for all receiver, it cannot learn M from the commitment. And the binding means that for all sender, after it sends the commitment to the receiver, it cannot change the message it commit in the commitment. So it cannot change M to M prompt after sending a commitment to the receiver. So it is also a very fundamental primitive. And then, the protocol is as follows. The protocol is as follows. So the proofer first commit the graph to the verifier, and the verifier just gives the proofer a challenge. The challenge will be 0 or 1. If it is 0, they just give you, you just need to give it the permutation of the graph. And if it is 1, then the proofer needs to open a cycle in the permuted graph. So you can see that if the proofer really knows the Hamiltonian cycle in the graph, then it can answer all the challenges, both challenges, right? And how about simulator? So simulator doesn't know the Hamiltonian cycle in the graph. So what it can do is that, okay, just commit the original graph to the verifier and get a change from the verifier. And if the change is fixed, then S can just rewind back, okay? And then it commit another graph, he know the cycle, and then send it to a verifier. And then, because the change is still the same, so it knows how to open the cycle or say open the graph to the verifier. So it finished the simulation. But in general, it can depend on the first message. For example, if V sees some other commitment, it may change the strategy to other things. So the idea in the Khurana protocol is that it asks the verifier to commit the change in advance. So it is a 4-message protocol. The verifier commit a change, the prover commit a graph, and then they open a change, and then the prover try to answer the challenge. Okay, and now we want to ask, like, why does not this GK protocol work in the quantum setting? So there are 3 properties that fail the GK protocol here. First, we can have an auxiliary quantum input. Like here, we can have some like quantum advice. And then we know that quantum not correlating 0, which means that S or P, it cannot copy this advice because it doesn't know the advice. And the measurement collapse the quantum state. For example, the V may try to measure its internal state at some point, such that it gets a totally different internal state that may influence the transcript. For example, here, let's send a commitment to the verifier first, and then the verifier measure its internal state and send a change. But right now, the internal state becomes another state, aux_prom. And then let's do the same thing, rewind back, and then try to commit another graph. But in this case, because aux_prom is different from the aux, so this behavior changes according to the aux_prom, so it may not give you the same change even if you commit the change in advance. And also the distinguisher, they may be able to check the internal state by the swap test. Say, okay, it is aux, not aux_prom, then the view of P and the S are different. So this seems to be a barrier to have the constant run post-quantum ZK. But we said that actually we can have like many positive results, but don't have the clean one. I don't know why this is cut. Okay. So right now we want to know. Okay, we have so many ways to get some zero knowledge, but not the original one. Then what happened? Like, why can we get like this beautiful result? And here we will show you the impossibility result. So we start from the Barak-Lindell theorem, which is a very famous classical theorem. This theorem shows that there exists a constant round strip polynomial time zero knowledge for MP. Then MP is in BPP. So here it says strip polynomial time. And actually the Khurana protocol, its simulation is an expected polynomial time simulation. And Barak-Lindell showed that you cannot achieve strip polynomial time unless MP is in BPP. Okay, and the main idea is that if you have such a simulator, then actually you can build a BPP algorithm for the language L. Okay, so let's try to do the reduction. This is a reduction that if you have a simulator, then you can construct a BPP algorithm for L. So suppose you have a strip polynomial time simulator S simulating any malicious V star. And then we just let V star be the honest verifier with aborting probability 1 minus epsilon. So which means that each time V star see a message from the prover or say the simulator, it just has 1 minus epsilon probability to say, okay, I want to abort the protocol. I don't want to continue. But if it wants to continue, then it just do whatever the honest verifier does. Okay. So here we have 2 cases. First case is X is in L, and the second case is X not in L. So for the case like X is in L, we know that PV star establishes probability at least epsilon to decay, because V star has epsilon probability to continue, and we have K rounds. The protocol is K round protocol, so the probability that PV star accepts is epsilon to decay, and which is a noticeable probability because K is a constant and epsilon is 1 over poly. And then this implies that as V star also accepts with probability close to epsilon to decay. This is by the zero knowledge property. So now we know that if X is in L, then S V star should also accept with probability epsilon to decay, which is noticeable. And in a case that X is not in L, in this case, because decay property has no guarantee for the soundness case, so we will have like two cases. The first case is that SV star sometimes accept with noticeable probability. And another case is that SV star always reject with 1 minus negligible probability, which means that and you can see that in case 2, which is a very good case because your SV star can decide L, right? Because SV star always says yes with noticeable probability when X is in L, and always reject with 1 minus negligible probability when X is not in L. So in this way, you can just directly use SV star to decide L, and such that L is in BPP. And how about, but it is possible to get into the case 1. So the next we want to show is that actually, if case 1 is true, then you can construct a P star, which is a malicious proofer, that can break the original sound, the negligible soundness, and such that only case 2 is possible. So L is in BPP. So next, we are going to show that how if we have a case 1, which means that SV star sometimes accepts with good probability, then you use it to construct a malicious proofer to break the negligible soundness. Okay. So now case 1. And so here, we use P star use the SV star as follows. So actually, you just simulate SV star by itself, but it randomly pick K out of Q queries. So here, we assume that S and V star, they exchange Q messages. And then because the protocol is a K message protocol, so P star wants to interact with the external verifier with like K messages, right? So you just randomly pick like K out of Q queries from these Q queries and forward these queries to the verifier. And then pretend that, and after get a response from a verifier, you just send a response to the V star here. Okay. And the best case is that if P star is lucky enough, he will get lots of abort when he interacts with the V star, but he always get non-abort when want to interact with the external V. So in this case, he still get accepting view from the SV star, but it doesn't need to actually interact with V star because like all the interaction between S and V star are just abort. Only the interaction between V and the S is non-abort. And so this is the best case, like very clean and easy to analyze. And the probability that this case happen is actually 1 over poly because we are trying to choose like K messages from like polynomial interaction. So it's 1 over poly, it's like Q choose K, so which is like still 1 over poly. And in this case, P star can convince the verifier with probability 1 minus poly, which contradicts the negligible soundness of the zero knowledge. So in this way, we can show that case 1 is impossible if you believe in the negligible soundness. Okay. And so this is the classical Berkeley proof to show that constant round strip polynomial times ZK for NP is impossible. And you may want to know, okay, can we get the Quantum-Berkeley theorem? Say we assume that, oops, yeah. Okay, so so let's try to do the Berkeley by just replace the bugs by quantum algorithms or quantum advice. So here we try to build a BQP algorithm for L from the quantum simulator. So here we suppose there exists a quantum polynomial time simulation and blah, 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 the same. And we still have the completeness and soundness case X in L and X not in L. And X in L is still like, the proof is still the same because like PV star accept, then by decay property, you can say SV star accept with good probability. And we also go into a case 1 and case 2, and we want to prove that case 1 is impossible with quantum machine. And here, the reduction becomes a little bit tricky because P star right now wants to do the SV star itself. And then based on the classical proof, P star needs to randomly pick K out of Q queries and forward them to V. If Q queries are not abort and the rest queries are all abort, then P star succeeds. But this is not good because it doesn't really hold if S queries V star in superposition because we know that S and V star, they may change like quantum messages. such that you don't know how to pick K out of Q queries from like quantum message, because P* needs to pick K classical queries. So we can visualize this here. So actually, here, P* when you run SMV star, you will get lots of superposition queries. And all these superposition, like part of the queries are abort, and part of it is non-abort. So you get lots of like superposition between abort and non-abort. And then how do the P* choose the messages and then send the classical queries to the external B? So it is unclear if you just like try to do everything like the classical Barlin theorem does. So the main idea is that actually you can measure the queries, and then after you measure queries, it will collapse to either abort or non-abort with the classical message, and then you can still like forward the message to an external verifier to get the proofs work. And why these two views are kind of like close is because of the measure and reprogram lemma, which is by Dunfer, Majans, and Schaffner. So this is a little bit like too wordy, but you remember that the last in equation shows that this view is quite close to this view with this particular factor. So here, which means that if you have a Q queries message and you want to measure a K message out of Q queries, then these two views are close by just divided like this parameter. Okay, so by using this measure and program lemma, actually you can come up with a reduction showing that you have many quantum messages exchanged between S and V star, and just by measure some of them, then you can get the classical message and use it to finish a reduction. And the probability that you are still good is still noticeable. Okay, so here is the reduction. So P* random pick K out of Q queries, measure a quantum query, and forward them to V. So this is the whole reduction. And then let's try to recap here. So here we run straight to, here we prove the theorem that constant round straight quantum polynomial times ZK for MP is impossible unless MP is in BQP. So this is by the framework of Barlin theorem, and then we use a measure and reprogram lemma. And actually using is not enough. You need like lots of hybrid arguments and more complicated analysis to make the things work. And yeah, but you can show that quantum polynomial time ZK for MP is impossible. And then the next thing we want to do is that we try to lift this impossibility result to expected quantum polynomial time. And quantum expected polynomial time means that, as I said, SB star might sometimes run into exponential time by finishing like polynomial time on average. So one possible activity of this like simulator is that it just runs sometime, and then you measure a bit and see if it needs to be stopped. And if it's not, then you continue rounding and then measure, continue rounding and measure. And in the last, you may stop some in exponential time, but on average, you can get it in the polynomial time. Okay. And so here we start from the first observation. The observation is that if S exists, its runtime must be related to the aborting probability if you have an aborting verifier. So why? Because S needs to see more non-abort queries to find the accepting transcript. Okay. So if S only makes Q queries and the V star abort with probability, say 1 minus 1 over Q to the 10,000, then S never sees an accepting transcript with very good. Never sees an accepting transcript, right? Because like too many abort, you cannot even finish the transcript. So we can say that the aborting probability here, if V star has it, is something that S can learn after a simulation. He can learn it very well by just say, okay, I do so many queries and I see some non-abort, then this is a good estimation about the aborting probability. But actually, P knows very little about the aborting probability. He only sees abort or non-abort, and then the protocol stops. So you can say that like in a simulation, S learns more about the aborting probability, but P knows little. So we try to say, okay, probably we can use this to come up with a malicious verifier. So we just try to let V star superimpose the aborting probability in its internal state. So this is the idea, but this is not totally correct, but I just give you some flavor about the idea. So first, P has some internal state 0, and V star have a bit saying that, okay, I want to abort with probability 1, or I want to abort with probability 1/2, and I make it a superposition. And then, as it is the same, a 0 internal state and a control qubit here. And after the interaction, P may know like almost nothing about the aborting probability. So its internal state is still 0, but because as he sees so many interactions with V star, so probably he can learn the approximation about the aborting probability. So its internal state will somehow entangled with with V star's internal state. And in this case, we can see that, okay, because V star's internal state is also included in the view of the zero knowledge definition. So this can be checked by the swap test. The distinguisher just need to say, okay, check whether V star's internal state is a pure state or a mixed state. So this is not a good case. So, but like this idea doesn't directly give you a formal proof. This just tells you that V star have the ability to do something more than a classical verifier. Because classical malicious verifier, actually it cannot do a superposition of aborting probability. You can just like choose the aborting probability and then use the aborting probability to interact with the prover or the simulator. But in the quantum case, we can somehow superpose the aborting probability. And this may cause some entanglement with simulator or with the prover. So we try to make it more formal, try to come up with a reduction. We want to show that if there exists a petty polynomial time simulator, then actually there must exist a strict polynomial time simulator such that for S in L, then this strict polynomial time simulator succeeds with noticeable probability. And based on our impossibility result by Quentin Baruch-Lindell, this is impossible. So you can say, okay, this is impossible. And how to come up with this? This one is by the idea we just said. Like we try to come up with a new malicious verifier that superposes the aborting probability. So now let's try to consider the following 3 different verifiers. The first one is the honest verifier. It is the honest one. And the V star one is the one we use in the strict polynomial time proof. This simulator do whatever V does, but with aborting probability 1 minus epsilon. And the second one is try to superpose, the third one is try to superpose the first 2 verifiers. So it has a control qubit, 0 or 1. And if the first qubit is in 0, then it just runs B. And if the qubit is in 1, then it just runs V star. So in this way, the V double star, this verifier, will abort with probability 0 in the first branch, and will abort with probability 1/2 in the second branch. Okay. And now we have the first observation. So if we have a petty polynomial time simulator with petty runtime Q, then conditional accept the this count register here of the PV star should be 0 plus epsilon 1. Oh, sorry, it's epsilon to the K1. Okay. And this is because after you measure it, and the 1 branch will just accept with probability epsilon to the K, but the 0 branch will accept with probability 1. So after conditional accept, the amplitude of this qubit will change according to their accepting probability. So 1 will become 1, and another one will become epsilon to the K. And of course, you need to normalize it by yourself. And then we just use the decay property, and we can see that the control register in SV double star should also be like 0 plus epsilon to the K1, condition accepting. Okay, so this is true just by the decay property. Okay, and then for the second observation is that, okay, but we also know that PV star accept with probability like 1/2 plus like epsilon to the K over 1/2. So this implies that SV double star should also accept with this, almost the same probability, say 1/2 plus epsilon to the K over 2. And then we just let S prompt be S that stops after 2 Q queries. Say we want to construct a strict polynomial time simulator from the petty time 1. And then it is not hard to show that actually S prompt to the V double star, a set with probability around like 1/4 by just Markov inequality. So this is second observation. Right now we construct street polynomial time simulator with V double star. And the last observation here is try to transfer this as V star to the simulator that just interact with V star. Okay, and we know that the probability that S prime V star accept is equivalent to, you run this, and then condition you measure the count register and you get 1, right? And this probability is actually epsilon to the k over 4. So this is still noticeable. And this is by combining like the first two observations. Okay. And so you come up with a street polynomial time simulator interacting with V star that accept with probability noticeable. And this finish our goal because our goal is try to, if we have a expected polynomial time S, we want to construct street polynomial time S prime that interacting with V star, its success probability is noticeable. So we finish a proof here. But there's another way to show the impossibility results. So let me go back. So here it is a little bit quite not the same as our intuition. Say the control QB are different. We use it, but in an implicit way. But we can use another way to see it. So now we change our goal. So it's another way to see a proof. So we want to say if there is a expected polynomial time S, such that we say their accepting probability is close, then their internal state must be far away. So the first observation is far from this. So say that PV double star set with good probability, then SV double star set with good probability too. And then by Markov inequality, we can say that S prime V double star set with good probability. Yeah. Okay. And then we have the second observation. Because we know that by the quantum Barrow-Lindell theorem, S prime V star only accept with negligible probability. Then by this observation, you can say that if you try to combine these two together, you can see that the internal state of SV double star condition accept is only 0 plus negligible 1. And this must be far from the 0 plus epsilon to the k 1. Okay, so this can also finish a proof. And the proof in our paper is the first one. And this one is our intuition, like how to prove the impossibility result. So let's try to recap and with hazard discussion. So in this world, we show that there doesn't exist post-quantum O1 round BBZK for MP unless MP is in BQP. But such protocol exists in the classical setting. And the reason that it doesn't exist in the quantum setting is that quantum B star can superpose some information that only simulator learns after a simulation. So this gives the quantum verified additional power to cheat. So there's no such constant round BBZK protocol. But of course, one can still bypass this barrier by doing some modification. For example, you use non-black box simulation construction, then you can get a constant round 1. Or you just sacrifice the noticeable soundness, or say sacrifice the zero knowledge property to epsilon zk. Or you use a slightly stronger simulator, which is called a quantum coherent simulator. Then you can still get constant round zk. But this one is good because it doesn't break any primitive. And one thing need to be aware is that all these simulations use the quantum rewinding technique, or say the Jordan's lemma Nick just introduced in the last talk. So this rewinding, let me just quickly rephrase it. So you just say that, okay, you have two projectors, then you can decompose the Hilbert space into one two-dimensional subspace such that these two projectors are invariant on these subspaces. And using this lemma, actually you can, you need this lemma to do like all these positive results. And then here I want to end up with some open questions. First, actually the quantum rewinding technique is very powerful, not just in zero knowledge, but also in QMA amplification, sustained argument, or even copy protection. People use this to prove something. And we want to see whether this can have like more application to other problems. And also, the same, like I think composition theory for ZK is a very fantastic problem. Actually, we have been working on this for a while, but we haven't been able to get very clean results about it. So Especially, we should focus on the unbounded sessions, CZK or PZK for MP, because actually we don't have any results for that right now. And actually, there exist such protocols. If you just consider bounded session, then you can have a polyron concurrent ZK for MP. It's by Ogawad et al. And you can also have post-quantum bounded session MBB, O1 round weak parallel ZK for MP. It's by Anans, Chong, and Laplace. And the reason that we cannot get this is because like all the current like zero knowledge protocols, we need to simulate like the aborting and non-aborting branch at first. And if you have, if each session you have non-aborting and aborting, then if you have like many sessions, then the probability that you get into the good branch is 1 over exponential, so it's too small. So we need some way to fix it. And another thing is that here we only consider like classical interactive protocol, but how about quantum communication or quantum primitive? Actually, if you allow the prover and the verifier use quantum to exchange quantum messages, it can also bypass. Our impossibility result doesn't hold in this case, but I also don't see whether it can work, or there may be some way to make it work in the impossibility result, or even construct a new protocol. I don't know. But I think it's an interesting problem to consider. Say, if you allow quantum communication, then can you get constant round ZK protocol or parallel ZK or concurrent ZK? So like here's a big table about the current status. So you have a classical ZK that we already know very well about constant round, unbounded parallel, and bounded concurrent. For quantum simulator, we know that constant round is impossible, but we don't know whether these two are possible or not. And for coherent quantum simulator, one, it is yes, but also question mark. And quantum protocol, all question mark. And you can consider other like MBB technique, epsilon, quantum zero energy, and so on. And it could be like many interesting open questions related. Okay, and that's it. Thanks.
Thank you very much for a great talk. Questions? We have time for a couple of questions. Okay, so let me start with one. I'm actually curious about the last thing you mentioned. Bypassing this impossibility with the quantum protocol. And maybe can you elaborate a bit more on why your argument fails if you allow quantum communication between the prover and the verifier?
Yeah, so the main reason is like the quantum Baroque linear theory doesn't directly hold in that case. So the reason is that, probably we can just see this graph. So the simulator may, how to say, the reduction, here. Yeah, this one. So right now the prover wants to interact with the verifier with quantum messages. So if it forwards some quantum message to the external verifier, it may entangle with some internal state of the external verifier. And then it wants to go back to interact with the V star here, then it becomes a little bit tricky because the V star have other internal state, which is not the same as V's internal state. But if it is classical message, then you don't have that problem because they don't entangle together. But probably there is some way to fix it by have a clever hybrid or something. We haven't thought about it very carefully, but it's just one barrier that we can have this to work for the quantum communication. Yeah.
So what do you believe?
Huh?
What do you believe? Should be fixable or there should be a protocol?
50-50 maybe. Yeah.
More questions? Okay, then we can wrap up and you can go for lunch. Thank you very much, and I hope to see you again tomorrow.
Thank you.
Thanks again, Nai-Hui.